Good morning, everybody. Welcome to CSCS. If this is the first time you are here, this is a big fancy building. You don't see any of the machines. The machines are in the other building. We might be able to get a tour later on during a break. I'll have to ask about this. But we're not here to look at machines. We're here to do some graphics and visualization. I am the visualization task leader here. I've used visualization for many years. I've used many different visualization applications. So why do I propose today the following softwares? Matplotlib, Visit, ParaView. It's because they're free, they're open source. But not only, because being open source sometimes means it's not well maintained. It's only one person in a remote part of the world doing a project. This is different. Matplotlib, Visit, ParaView, there are big projects maintained by a large community of developers and enthusiastic graphics and visualization users. So this is what I recommend. Furthermore, we are in a university environment, so I'd like to propose tools that people can just install very freely without having to require a license. That being said, you can have your favorite, one of your favorite tool at the end of this tutorial installed on your laptop, and when you travel to a conference, it's very easy. You want to show your work to a colleague, you open your laptop and you launch the software, and you're done. So no license, no. This is quite important, I feel. So already this is not working as I intended. The wireless, you've noted it already. So there's the agenda. Setup, objectives. Then we're going to look at this matplotlib library, which is a Python library to do 2D, mostly 2D, usually 2D graphics. The type of graphics you want for your publications, okay? Because it's actually very seldom that I see 3D visualization inside a publication. People expect a nice XY graph, a nice plot with nice legends, etc. That's what you need for publication. However, it's probably the case that to get to the 2D data that you need to plot, you have used some large 3D simulation behind it. And by the way, we are in a supercomputing center. So for me, when I talk about data, I assume the data is large. I assume you're doing some big computation. Otherwise, you shouldn't be at a supercomputing center, right? Now, how big is big? How large is large? Many years ago, my colleague Jim Ahrens from Los Alamos gave the following definition of large. And I think it fits quite well. Large is what doesn't fit on the computer you're using on your desktop. So if you have a fancy Mac with 16 gigabytes of RAM, large would be 20 gigabytes. If you're using a palm top, a hand device, large is probably smaller. If you're using if you're using a cluster, large will be perhaps a terabyte. And if you're using ROSA, which you can today at CSCS, and Daint, which is the next crazy supercomputer that will be made available for the public, then large can be petabyte. Okay, so what matters is what tool you're using to actually do your graphics. Matplotlib, and we're going to do some exercise, and here, of course, we have to start from simple things, so the people who have already practiced with it, bear with us. We'll take a break because all of us, including people here in Lugano, have gotten up early this morning to arrive, so we'll need a coffee and a break at 10:30. Then I will talk about visualization pipeline. Because it's an ubiquitous term, I will talk about pipeline, or I assume the notion of this visualization pipeline are known for the rest of the 2 days of presentation. When we will see the ParaView and the Visit software, they implement a visualization pipeline. However, it's hidden, which is good from the point of view of the user. However, many times, in fact, I have users tell me, this doesn't work, and yet I've done everything right. Well, it's because there are issues with this visualization pipeline that people completely forget, and then the system is not dimensioned correctly to actually do the visualization. We'll talk about VTK and some examples of charts and info visualization, because VTK, which is this C++ toolkit, which is more than 20 years old now, it's really a mature toolkit. VTK has also expanded into the realm of 2D graphics and non-spatially related data. So this is what we call the InfoVis data. We'll talk about data formatting, because many times, especially new users at the computing center, will make, let me be frank, will make the mistake of inventing their own data format because it's just more convenient. I understand it, so there. I do it this way. But then we cannot use the visualization softwares we have available because we cannot read this data. So we're going to learn about how to write proper data to be able to facilitate this transition from simulation to visualization. And really, I said transition, but I always think about visualization as being an integral part of your simulation cycle here. So you run some simulation, you produce some data. Visualization is just one other step of your process. There will be a lunch break. And then we'll talk about ParaView. ParaView, so we only have an hour, which is not much. I've taught ParaView tutorials that were going on for 2 days, you can imagine. But the essential we're going to learn, and one of these essential things is how to use ParaView from your remote location, wherever you are in Switzerland or across the world. Then we'll talk about architectural issue and big data. We'll have a break, and then we'll talk about exactly this client-server business, how to run simulation remotely. And then finally, we'll talk about interactive session versus batch mode computing. Now, all of the batch computing we're going to do for the next 2 days is Python driven. However, you don't have to be an expert at Python. I am not. Okay, I tell you immediately, so you know the setup. But we need to know the basics of Python. And then we're going to use Python from this morning until tomorrow afternoon everywhere. And we're going to learn how to have the visualization application write the Python code for us. This is why we don't need to be experts. The applications will write the code, and then we'll have to do some fine-tuning maybe, or we'll have to do some additional work to make it consume data for a time-dependent simulation, for example, but nothing difficult. So this is also one of the big objectives of the tutorial. You will know how to run Python scripts for ParaView and Visit in batch mode computation by the end of this tutorial. And we'll have some simple exercises that will work for you, and then you'll be able to apply those simple examples to your specific data. This is for today. Tomorrow we'll repeat more or less the same schema with the visit software. And then after the break, I've got the following items, but I kind of want to leave it open because I want to see how you, the audience, react to things. If you're asking interesting questions, then I'd rather answer those interesting questions. How do we do this and that? And if it's not in the notes, I will make it happen so that those questions are answered. However, at least the middle component here, the in situ visualization, I will show, I will propose, I will demonstrate, because I'm a co-author of it, and I like to push it. I like to push more people to use it. This in situ visualization is really what I said earlier, is to accomplish what I said earlier, binding together the visualization and the simulation. Instead of writing data to disk and then reading the data back into a visualization software, we're going to link that together. We're going to make the visualization happen at the same time as the simulation. It's very powerful, which means eventually that you don't have to worry about file formats. There's no more formats. You don't write data to disks anymore. You connect your simulation data to the visualization. It's quite powerful. So I'll have some examples, and then we'll see about this. Okay, I've consumed, I think, my allocated time for the introduction. Visualization service, you can click to this link, and you can see about what we do in this service. These are the things I just said. And yes, we will use many resources on the web. You know how rich the web is with tutorials, examples, and questions. Every time I have something I don't know how to do, I just go to the web and I ask the mailing lists, the wiki, etc. This is something I need to encourage you to do even more. I forgot in which page I have. Let me look, because the notes are available, but I forgot where I put it. There we go. So if you can already connect to CSCS, and maybe I'll give you a few minutes to do this. Oops. There. Using the course ID that we've given you and the password. Accessing Eiger. Perhaps I didn't say it, but you need to SSH to ELA first. Or can you access directly? I don't know. Okay, good. So go to Eiger. Oh, sorry about this. And in this directory, project, CS staff, courses, CSCS graphics and visualization 2014, you will see 3 PDF files, which are the course notes. There are 3 for the first 3 half days that we have, and like I said, for tomorrow afternoon, I like to leave it open, so I will make the notes tonight after I see how things are going. I'll give you a few minutes to SSH to the right place. Yes? Okay. Yeah, yeah. So did you use that ID we gave you?
Yeah, even pinging, it doesn't...
Temis, are you in?
Yes.
Ah. Did you use this course thing?
Yes.
Okay. Anyone else has problem? It works. It works. I don't know. Close it. Try again. It works for everybody else. No. There's no need for VPN. You should just be able to get in automatically. Ma mi dicono di no? Sì? Sì. No, I have bandwidth here. There's no need for VPN.
That's the problem. With VPN, it doesn't work.
Ah, okay. And now does it work? Okay, good. So why are we here for visualization? What is the visualization? I want to spend a few words about this. Yes, we will do 2D and visualization on the desktop because that's very important. And then we'll talk about 3D and large data. So all the issues related to large data, client server, remote, parallel, in situ. Visualization, I consider it at least 5 different things. The first one is data exploration. So you are building a simulation. You're building an algorithm. You're not sure about the quality of your simulation. You just need to explore things, test things. This will be the very first activity. Second one is the one you will need for your publication, do the nice plots. This is really a 2D, mostly 2D activity. Third one is visual debugging, and this is a place where you might want to have in situ visualization, such that you can run your simulation, visualize it as it goes, perhaps do some modifications in real time and see the effect of this. Then there is a lot that I'm interested about with comparative analysis. For example, look at the difference between time step n and time step n+1, or look at a simulation of a Navier-Stokes solver versus an Euler solver, or look at the last 30 years of simulation, and then look at the next 30 years and do an average over multiple time steps. So comparative analysis can really be, can have a lot of flavors. And then presentation graphics is usually making a movie. Now, I'll be frank again. I mean, I love movies, but I only do 2 or 3 every year because it's a lot of work. You want to make a nice quality movie to show at a conference, start early. That's my advice, okay? However, if you want to do the quick movie to show to your PhD advisor or to show to your colleague or to send across the ocean to your friend, making simple movies, that's not difficult. And this you also should be able to do at the end of this tutorial. What I say is difficult is when you have to start putting labels on the 3D graphics, when you have to do smooth transitions, when you have to do all those things. And to make a nice movie, you should be doing it at HDTV quality, which means high pixel resolution, which means more computation. And this is kind of a spectrum of things that I have done in the past. You see, from atomic scale simulation to astrophysics, any scale I'm happy to work with, okay? I can't say I have favorites because they're all good problems. This picture here is actually interesting because it's not a good quality image. This is a screw, okay, a screw model, and perhaps you can see those lines here, dark lines, which don't have any physical meaning. This is an artifact of doing parallel visualization. This is an old image. I now know how to do it better. Okay, but this is to tell you that I spent actually a lot of time dealing with those boundary conditions of doing parallel visualization because it's not trivial, it's not simple to do. Okay, we're going to use Python. There's also an additional tool which you might want to start using if you don't already. It's called Ipython. Ipython is an enhanced interpreter for Python, and I really recommend it if you don't already have it. On Eiger, to make things simple, we only have Python. We actually have a recent version of Python, so that's not so bad. We have 3.3.2. And in the README file, which you're supposed to read, there is the instruction to add to your path the correct Python directory to execute our examples. Then, the two softwares, ParaView and Visit, can be downloaded from those particular sites. And perhaps during the lunch break, this is something you can do if you haven't done it already, is to start installing the ParaView software, which we will use this afternoon. So your only task is simple, is go to the website, install a pre-compiled version of ParaView for your specific architecture. So if you have a Mac, if you have a Windows, 32-bit, 64-bit, Linux, you pick the one that fits for your desktop, and then you install that. Okay. This will be useful when we test connecting your laptop to the CSCS computer. But this morning, we'll be able to do everything on Eiger. So I think we should get started with the exercise. And to do the exercise, I will need to demonstrate how to go to Eiger. Okay. So here I am in the right place. In this particular directory, project, CSCS staff courses, there is a shell script which Angelo here at CSCS has developed for us to use. And if you submit this particular batch script to the system, it will allocate a node for you and then launch a VNC server on that particular node. With that particular server running, you can connect. Here I'm assuming that you have some kind of Vnc Viewer available on your laptop. Or did I assume wrongly? How many of you know about VNC? Okay, that's not a large majority. But I've tested all those examples with SSH minus X, and they should work. So for those of you with Eiger, here's how I will run it. sbatch Eiger. as you can tell, it creates a file called temp turbo vnc Iger 240, and it tells me that this particular node has been allocated to me with the display 1. Okay, so Iger 240. If I run my Vnc Viewer at this particular address, and here you can use different Vnc Viewer tools available on the web. I use the Tide VNC here, which works very well for Windows. You have to create a password for yourself. And this password is, you create it for yourself, VNC password, and then you decide the password you want. Okay? This is left for you. And when I have a connection to Iger, then I can create any terminal and then look at the modules available. At CSCS, we use modules, all right, to set up particular compilations and runtime environment. Those modules will load the compilers that you need, the tools that you need for your job. So in this particular case here, you see I have the programming environment GNU, which is loaded here. And the important thing is to get the correct Python. So in the file, README, here I have this highlighted for you. This is the Python you need to pick up. I don't know if it shows very well in black. This is the path. This is the correct Python you need to set up for the experiment. Then in that directory, I have Python, and I have matplotlib. Now, those examples we have for matplotlib, they're taken from a very nice tutorial made at INRIA in France. And there's something important about running those examples is the following. Interactive updating. If you run Python followed by the file name for all of those exercises, you'll get the full set of instructions executed and loaded, and you'll be done. You will not have a way to interact with the plot. So at that particular address, matplotlib uses shell. There are the instructions on how to do an interactive session. You don't have to go visit this site immediately. This is for reference because it's actually very, very simple. There are two commands to type at the Python shell. I on, parentheses, which means interactive on, and then I off, which is interactive off. I will now do the demonstration of it, and you will see how trivial that is. All right. In those matplotlib in this matplotlib directory, I have a set of exercise, which I will put up in an editor here. And we'll start with the very first one, okay, which I think I can bring up to here. There we go. Now, the people, some of you, if you have Ipython, you can run Ipython with the -/pylab option, and then automatically you have pylab. Pylab is this sub-module of Python which lets us do the plotting. If you don't, here's how we're going to do it, and it should be pretty simple to follow. We start our Python editor, and then we can start typing those commands, which we can also cut and paste. But just to show you the example, this is the requirement for the exercise. If you are capable of running Python and typing from pylab import star, then we can do the whole exercise. Okay? And those commands are exactly right here. So as you do this, make sure that you have in your Python window, you have the 3.32 prompt here, which indicates that we are picking up the right version of Python. Now, just to get you motivated here, I will cut and paste those commands. There. So you have it. At least you're motivated now. You know what we're trying to do. We're trying to do this simple plot. Okay? And now we're going to dissect a little bit those commands, but you will see that there's nothing really difficult about it. So the ION command here is to turn the interactivity on. Here, I allocate 256 numbers, and I use linspace. So as you know, in Python, the pylab and the matplotlib libraries, they mimic the function names of MATLAB. So those of you who are using MATLAB should recognize those names from MATLAB. Yes? Did you update your path?
So it should be
No, there's no module load Python. There's no modules for Python. There's simply a path to it which you find here. This particular line here, you have to use path. We have to put ahead of our normal path the directory apps Python. So what I suggest you to do is to put that into your bash file, your bash RC file, and then for the rest of the tutorial until tomorrow, you'll have it set up already for each interactive sessions. Okay? So assuming you have the correct path to Python, then we should be able to get to this particular graph here. So when we run matplotlib, we automatically get the NumPy library. Okay, that's another important point. And NumPy is loaded with the default NP name. This is why when I instantiate an array of size 256 in between -pi and +pi, I use this particular syntax here. So linspace is just a linear array between those two bounds. In fact, just to show you the array, we can just print it on the screen. As you can tell, we have an array of numbers of size 256. And that last number is indeed pi. And then the first number would be minus pi. There we go. Okay, x of 0 is minus pi. And x of 255 is plus pi. And what we have on the screen is an array called C and an array called S. The first one is cosinus of the array X. The other one is sinus. And by simply plotting X, or I should say C as a function of X and S as a function of X, we have the particular plot here, the cosinus and the sinus on the screen. So if we manage to make this first example work, then all the other exercises are just incremental things following this first exercise. So we can spend some time here to make it work for everybody. Yeah? Tell me the... You cannot? That's because you, well, then just use another terminal, another editor like VI. And you can, yeah, simply. What I recommend is simply cut and paste those few Python commands to your Python interpreter.
So if, well, I tried to start a Vnc server to get what to put here, but it didn't work. And if I try to do the exercise, it throws me back to the something like this. I didn't go there, but because we're all in your directory, I tried to copy it in Scratch.
And you cannot copy it?
Some of the stuff
Yeah, what I didn't say is perhaps it's safer and more useful for you to copy those exercises to a private directory of your choice. You don't have to be, there's nothing specific to that directory. You can copy all of those Python scripts to your home directory. So, problems, yes. Here.
I've got about this VNC.
Okay. Let me answer other questions first. This is already a good step. Yeah. Yes.
I think I have a display problem. That is some mistake.
Interesting. This.
I think
SSH minus X.
Yeah.
You did it.
for but for Iger, I did
No, you also need a second one to Iger.
Okay.
Yeah.
My mistakes are
But
not
you
there.
should have been able to access Iger directly. Did you try? So try to maybe quit this session, go directly from your terminal to SSH -X Eiger, and that should be okay. I see other people here, they have it running on the screen, so this is good. Yes, okay.
So I don't get this VNC
Uh,
I don't have it on my machine.
yes, you do. I look here. Ubuntu.
Yeah.
In that case, go to Synaptics. Those of you running Ubuntu, if you don't have the VNC Viewer, go to run Synaptics. You don't have it. Then you come here to Systems. Actually, I forgot the name. Oh, Archive Manager? No, that's not it.
Oh, where you install system.
Yeah.
Install,
I use Synaptics. What's the other? Yeah, there it is, Synaptic. Okay. And then here you search for VNC. Here, VNC. There we go. Try to go down the list. GNC. Or try to type VNC. Tight. Yes, VNC. There we go. X-tight. This is what you need to. This is what I recommend. This is the one I use.
and now I can install it.
Make it, yeah. Mark for installation. And then say apply.
Okay.
Apply. So I forgot. What was the name? The name was.
X type VNC.
Yeah.
And then I just start.
Yeah. Once it's installed. So I'm making here a parenthesis. For those of you trying to install the VNC Viewer, if you're using Ubuntu, run Synaptic, search for tight VNC, and then install the package. If you're using Windows, I recommend doing a Google search for tight VNC or for VNC Viewer and install the one you find. This is the way I've done it for my own machine. Okay. Now we need to move ahead here and continue with those exercises. So as you notice here, I have a full Python prompt here ready. Okay, so I can in fact interrogate and go back in history to see what has been executed, modify things, etc. So at this point, I'm able to modify the plot I currently have. So this is exercise 1, and this is the first figure you should have on the screen. If you go to the second exercise, the second exercise actually repeats everything as the first exercise, except that it explicitly sets several variables to their default values. So here, for example, we create a figure, we create a subplot, and all of those were done automatically by the first exercise. Here we instantiate color blue for the first graph, color green for the second one. There is a particular line width that is used, and align style. The limit of the grid in the x direction is -4 and +4. And as you can see, this is exactly what we had here on the graph. The tick marks were set up with a step of 1. So this is what was done. In the right direction, we have limits between -1 and +1 with tick marks every 0.5, as you can see here in the vertical axis. So basically, if you run exercise _2, you have everything with an explicit instantiation of all those default values which PyLab uses. If we go to exercise number 3, then we're going to change a few things. So we could very well do a CLF which cleans up the previous figure and instantiate a couple of plots like this. There. So what have I changed? I've changed the line width and the color of the particular plot. Instead of using blue and green, I use blue and red and a line width of 2.5. This is the first change we've made. And then we're going to slightly change also the boundaries of the graph to make it more easier to see. So there we go. There, I have a little bit more room on my display. And this is what I encourage you to do now, is to go from exercise 1 to exercise 10, and there are incremental changes every time we make the graph more fancy, more pretty, if you want, with more annotation. So for example, if I were to go to the exercise number 4, here the only thing that changes are the limit again of for the tick marks and all. So here's how I run it. What I've done is I've added a little bit of room at the bottom here and on the right and the left side of my graph. Okay? And this was done by multiplying those bounds by 1.1. So I've added 10% if you want on each sides of the graph. If I go to exercise number 5, here I'd like to replace the tick marks, the labels, by the value pi, the mathematical symbol for pi, because this is what really it is. So we are able to do this by changing our tick marks again with the following commands. Actually, I'm one step ahead. Here, what I've done is I've put the numerical values for pi, minus pi, and plus pi. But eventually, I'd like to put the symbol. And this will be the demonstration of the next exercise. And we are able, using matplotlib, of using some LaTeX type annotation for symbols. So if we copy now from exercise number 6 in our particular window in our Python interpreter, there I have now in my plot, as you can see, the horizontal axis clearly shows minus pi over 2, plus pi, etc., using using mathematical notations. So this is getting more scientific, right? This is almost ready for a publication type quality display. Am I going too fast, or are some people completely back? Okay, this is working good. Okay, you got all your notation. Yes? Perché no?
Un errore Favre qualcosa.
Fammi vedere l'errore.
Non so se nel punto startup.
Non vorrei che sia... è perché io lo uso già il 241. Perché
No,
sì.
non c'è mica scritto di andare sul 240.
Già. Sì, ma non lo puoi girare da qua, perché non può scrivere il tempo. Devi fare una copia locale.
Sì, no,
Ah,
fai nella sua.
la sua 1.
C'è una copia.
Ah, ok. Dov'è l'underscore? Ah, ok. Ups. Questo ci vuole... Manuel. Alcuni ci sono già, ok.
Lì è
01 e non parte proprio. Perché no, è un underscore. E underscore.
Metti il D5 lo segno, 7. Minus 7. Dovrebbe chiedere di espressione.
Sì.
E non, secondo me non finisce.
Ah, ok. Out. Perché non c'è un Eiger? Ah, sì, Eiger 200.
Devi vedere qual è
SQ, oddio. Meno L. Ah, ecco, 180, il 180. Aspetta che...
Perché sono sporchi quei cosi.
Adesso lo spiego al... Okay, I will add another slide here for people doing VNC. Okay, for people doing VNC here, I've told you to copy the batch script Eiger to, for example, your home. And what you do is when you submit this job here, you need to find out the name of the machine that was allocated to you. This is very simple to do. You type the command SQ minus L. Let me show you again. Okay, SQ minus L. And here it shows you a list of all the nodes that are allocated. So you simply look for your name and then you look for the name of the machine that was given to you. So for example, if I take myself here, I have the job 6091, fine, and the machine Iger 240 was given to me. A temporary file is created called tmp Iger.40, and it gives you the display, the display ID that was allocated. Oh, not again. Okay. Ecco, Jean Favre, J Favre at Iger 240, column 1. So in my VNC, if I quit here and start again my Vnc Viewer, this is exactly the address I have typed, Iger 240. You need to add the name, .login.cscs.ch, column 1. Okay, good. Lots of graphics here.
Yeah, but this is just through the X
Okay.
forwarding, so I want to
Okay.
try and.
That's fine too. You can. So you're ahead already. So you okay? Good. Good. Problemi qua.
Sì, no, in realtà stavo lavorando in locale, quindi non
Ah,
è
ok.
un problema.
Ok.
Però ero semplicemente curioso, in realtà non trova...
No, non ho sbagliato qui. Devi aggiungere il column 1
Qui
con il,
dentro.
sì, con il numero del
perché-
display. Sì.
Perché è definito qui.
Ah,
Vabbè, quello lo mettevo,
scusami, questa è
Figurati,
l'interfaccia,
non è che sia, sì, una...
l'interfaccia Mac.
Sì, sì, guarda,
Non lo
è-
trova. No, dot login. Iger 201.login.cscs.
Scusa, ok.
Yes.
Know how to get the display number. So I run the job.
Yes.
Slash being slash.
So your name, so you got 181. Yeah, don't run it multiple times. Huh? Okay, now in your directory here, there's this file called tmp. Look at tmp.turbo. No, the one below,
Oh, yes.
slash dot out. Okay, there it shows you 181.column 1.
Okay.
So you will need to type into your VNC viewer the name iger181.login.cscs.ch column 1. No. Don't. VNC viewer, I don't know this minus name thing. Type Iger 181 dot login dot cscs dot ch column 1. Ecco. There, you put your password.
Okay. Yes, I
Oh, you use the
I
same
did my
one.
best.
Okay, fine. There,
Okay, thank you.
perfect. So you can teach your colleague here next door. Yeah, here. Okay, just use SSH minus X for now. Is this working?
Yeah.
Okay, good. So let's see VNC then.
VNC, I used VNC.
Okay. Yeah, so the address to type is actually iger242.login.cscs .cscs.ch comma one, not comma, double point 1. There. Okay, your password, your VNC password.
Oh, what? This I didn't get.
Oh,
This
then
one.
no, then try no password at all, or
Okay.
I don't know. No, I guess it needs a password. Go back to your Eiger place. Here, type VNC password. VNC password. Okay, give yourself, come on now, this. You need to load the module
Okay.
turbo VNC. Module load turbo VNC. Turbo VNC. Okay, now type VNC password. Okay, good. Return. Give yourself a password. Something simple, doesn't have to be fancy.
Did what you mentioned, so I copied the I got
Yes,
VNC
yes.
to that thing, and then I patch. So I have
Okay.
this, here. Now you said something about copying a VNC, something like.
Have you done the exercise yet?
No.
Okay, so this is more important. Let's do the exercise first, which should be very simple. So you've copied the Python files, have you?
No, so I should copy them from the.
Yeah, it's easier if you copy them over to your
Okay.
place. Here, do you have problems?
Well, I don't know. Well, I cannot visualize everything.
Oh, good.
But if I need VNC, I don't know. It's just etc.
So this is working at least.
Yes.
Have you been able to do the next iterations of the exercise? Okay.
Then like VNC, right? Because
No,
I
no,
did
for
some
this
scripts.
you don't need it at the moment. Yeah.
Basically copy everything in this actualization 2014 into.
If you want, yeah. If you want, yeah. Yeah, it's very light anyway. Ok, funziona, sì.
Sì, ho un problema con il mapping. È una cosa carina. I caratteri sono diversi, per cui.
Ok. Te lo faccio vedere lo schermo. Strano però. Okay, if you pay attention here for a minute, and at this particular link here, accessing Eiger, I have a page that is important to read. Remote visualization access. This is for people who have problem with VNC. At the bottom of the page, it says important. Your file, etc., must include at least this. Point B, etc., etc. This should have been done for you, for all accounts, automatically. If there was an error for somebody, I apologize for it, but this should have been done, and this is what determines the mapping of your keyboard. For some of you, I mean, at least one person here, whatever you type on the keyboard shows completely garbage on the window. This is a problem with the terminal mapping. But besides this particular solution here, I don't have. I don't know what is to be done. So this particular link you find on page 13 of the tutorial notes under accessing Eiger. All right? Just for the sake of the persons who are ahead with the exercise, I will now continue with exercise number 7, and I can more or less do this CLF to clear the screen and start from scratch with that particular instantiation of the exercise. This is exercise 7 there. So what we have added in this particular map are now some more annotation. Okay. If I go to 8, I now have a legend here on the left side of my graph. If I go to number 9, you've seen that I've added some notation, a particular point here on the graph which I want to emphasize, some arrow. Here, this particular dotted line is done very simply by doing a plot of a linear function in the vertical direction using the dotted line style. So there it is. We use the function scatter. I want to talk about visualization pipelines. A pipeline will be exactly this. A set of modules connected to each other. It will assume a downstream flow of data between the data in this module to the next module, etc. Let's see in more details what this pipeline is. Now, usually it's a data flow network connected in a directed graph. And then we have 3 types of modules: the sources, the filters, and the sink. So the renderer here, the graphics window, is usually a sink, because from that there's no more flow of information, or we can save the data to an image file. So an image writer would also be a sink. Anything else in between is a module. So modules are functional units. In this case here, I show modules with one connecting port going outside of the module and one input into the next module. But we can have some modules with multiple inputs here. And we can also have one output going to multiple modules. So we can branch out to sub-pipelines if you want. The connections are directional. And both in the case of VTK ParaView Visit, it is bidirectional, which actually means that there will be information going downwards and also upwards. And then the last thing that matters is the execution protocol. There can be a protocol that is event-driven or one that is domain-driven. Domain-driven would mean that I can set up a full pipeline and nothing would actually execute it until I explicitly demand execution. And this will be very important when we do large-scale visualization. Okay. Here's how visualization pipeline work. The source of the data, which is usually a data reader, this data reader should know the characteristics of your data. The size of the grid that is to be read, the number of time steps, the number of variables that are available, the type of each variable. Do we have scalar, vector fields, tensor field? Is it floating point? Is it etc.? Whatever information is useful to describe the data, but not the data itself. And this is what we call the metadata. And usually, this metadata has a region information. So the model you have occupies a certain region in space, and this model also has a certain indexing order. Okay, ij in 3D, ijk running from 0 to 255, etc. This information travels down the pipeline all the way to the sink. This is the first step, and we call it an information update state. In other words, the heavy data has not been loaded yet in memory. What travels down is only information about the grids to be loaded. It's the metadata. The update, the sink here, at this point, decides what update it wants to do, decides which part of the data it wants to load, and that information travels back to the source. So it's an update request, if you want. At this point, the pipeline is fully ready to execute, and the heavy data is actually read and creates a particular data set in memory. This data set is passed into the following modules, and the heavy computation actually takes place. So, of course, the first two steps here in the visualization setup, they are almost instantaneous. You don't see, it doesn't take minutes of execution to do this, unless, actually, I have a good counterexample of it, something that you should avoid at any cost. Here's the example. If you have a time-dependent simulation, and if you're going to store each of your time steps one after the next in a file, I mean, that seems like something very natural to do. Except that if you give me that file, how do I find out how many time steps are available? I don't know, unless maybe as the header of the file you say there are 1,000 time steps in here. Otherwise, I don't know, and I have to read the whole data set just to discover what is inside the file. So this is something we need to ban absolutely from your practice. If you're doing something like this, you don't have to raise your hand, okay? I'm kidding. This is the type of a file format that should be avoided absolutely, because they would cost a lot of time just to discover the metadata information about it. There. So we've learned at least that much. Now, if I look at the pipeline inside of the ParaView window, and we will see this in more detail this afternoon, we're going to see something like this. So in fact, we have here a multi-branch pipeline with a source of data here at the very beginning, one filter directly connected to it, and then the same output goes to a sub-branch of the pipeline. We do a contour, we do a histogram, and we do an extract edges. This is the view inside the pipeline browser. Remember this model. So now the Python syntax to actually create this pipeline would look like this. Any filter, we need to set its input connection to the module that is above. So if we have here a filter and a source, we get the output port of the source, and then we feed that to the input connection of the filter. The same thing for the mapper, set input connection, filter, get output port. So those are actually the two fundamental commands of Python that you need to learn to create your pipeline. You will assemble your pipeline with multiple elements. However, when you do this interactively in ParaView, this syntax will be hidden from you. Okay, but it's good to have in mind. Now those filters can be hundreds. Here I have just a few examples of them. So the contour, which would be the isosurface evaluation. Threshold, which means the extraction of a particular scalar field within a particular set of limits, and etc. Now we have to keep in mind that when we execute a certain filter on a source of data, we might actually create a lot of memory internally. Let's go back to this example here of the source and the filter. Imagine that the source is a large three-dimensional block of data with a scalar field. If the first filter I put into my pipeline is a threshold filter, which says I want all the data that is within 99% of this particular threshold, what will happen in memory? If I have a terabyte of data in memory, I will have a second terabyte of data with this scalar field slightly less than the original data set. So the pipeline, as we know it, is actually a big consumer of memory. Okay? Just because some of these some of those filters can actually create a whole copy of the data set. Let's take an example that is different. If you take a slice, a cutting plane through a data set, in that case, there's relatively little memory impact because we start from a 3D block of data and we create a two-dimensional slice. So if you take a terabyte of data, you slice it, you only have maybe a few megabytes in a slice. Okay? So keep in mind about the memory consumption of your pipeline. So this, I have explained that we have a bidirectional flow of information. The rendering is what drives the execution, so it is demand-driven. And the key Python command to execute is actually to take the name of the viewer and to say render. And we will see that there's a big difference in ParaView. We will see this afternoon. Building a pipeline interactively, because when you build a pipeline interactively, you first create the source, and then ParaView will read the data and show you a representation of your source data already. Then you add a filter, and ParaView does a second execution just to show you the representation of the filter, and so on. Whereas if you build your pipeline using only Python command, you can delay the execution of the rendering until the very end. Because when you use a Python command terminal, you create your pipeline, but you don't request any, there's no viewing that takes place. So you are free to build up your pipeline and then finally, only at the end, say, draw the picture. And in this case, you have a single execution through the pipeline. This is actually a case which I use very often with very large data. If I do a pipeline construction interactively, I cannot manage. It just blows out of memory. And if I do it with Python, I delay this execution to a single execution of the pipeline, and things fit in memory perfectly well. All right, so VTK is just, between quotes, a C++ library, so there's no really a utility for it, or there wasn't until version 6.1, which is being released right now as we speak. Version 6.1 includes a particular shell interface, and it's called VTK Python. If you go to this particular website, you can actually install already today the release candidate 1 of the VTK Python. It can be a tool to use interactively at your desktop. Now, on Eiger, I have actually compiled VTK Python, and I have embedded it into the ParaView compilation and into the ParaView module. So if you are loading the ParaView module, you automatically have the VTK Python shell. Here's the example of installing this VTK Python on my Linux desktop. If I do this, and I install it in this particular area, local apps, then this would be the arguments to type at your console to run it with Python. So I use Ipython. Oh, shoot. And here's how I do it. I set my library path to the directory Linux lib. I append to the system path that particular Python path, and then at this point I am able to run any VTK example loading the VTK module. So this gives you a VTK shell Python prompt. But we need, how do we start? We need to build visualization pipelines. We need examples. We need data sets. OK. So I've listed a couple of sites here. And in the notes, everything that you see in red, there are actually links that you can click directly. All of those links should be active. If you open one of them, it opens your browsers to the right place. Now we have another difficulty is that not all examples are yet compliant with VTK6. So we need to check that out. Otherwise, we go to the GitWeb subdirectory, and here we get the full source code available. On Eiger, in loading the ParaView module, we are able to exercise some of these features by going to the Python directory and the VTK subdirectory. So here's an example that is quite verbatim about the visualization pipeline. So a source. In this case, I'm going to draw a sphere. And actually, let me run it for you. Yeah, I will copy this, run it on my desk here just to show you how it actually works. I think it's always kind of difficult to cut and paste to an a Windows terminal, but I think I can do it. This is copy. And here's my VTK prompt. There we go. I have it running. So there is my visualization. Nothing fancy. It's a sphere. I have shrunk the elements to make the backside visible. Okay, there's no coloring, there's nothing, but at least I think you understand what's going on. Here's the pole of the sphere. There we go. So how do I accomplish this? That's my pipeline here. I create a sphere source. So all the class names in VTK are prefixed with VTK. So this is this is a VTK sphere source. Then I need to shrink the external surface of that sphere. So it's called a VTK shrink polydata. And there is my syntax. Set input connection, sphere, get output port. So I have connected the source to the filter. Then I get a mapper for it. A mapper is what creates the geometry object. The mapper uses the same syntax, set input connection, shrink, get output. So I've now built up my pipeline up to here. I create a renderer. And at the very bottom, there's a few more decoration here to get an interactive renderer. But at the very bottom here, I do a render, and this is what executes my pipeline. So these examples we have on the Eiger directory. However, since we're having some problems of execution, I'm not sure everybody can execute it. What I have done here on my laptop, I have installed the VTK Python shell from that directory. And as you can see, I'm running here locally without connection to Eiger. This is my interactive shell. There. And here at this point, I have, you see, a very, very dumb terminal where I can type commands. To quit the VTK renderer, I think I have to do escape, and the Windows, it's not behaving very well. All right, so this is my pipeline in Python. It's a lot of stuff, actually. And your question should be, how do I find out the names of those classes here? Well, you learn by practice. You learn via the examples that are on the web. But better yet, with ParaView this afternoon, we'll see that we can instantiate the same pipeline and have ParaView write the code for us. And then we have something to cut and paste and to adapt to our own needs. Now, this was just to finish a little bit the discussion on charts and InfoVis. And I want to show you a couple of graphs. This is from the Kitware blog. A couple of visualizations of data that is not grid-based. In this case, it's tables of relations. Okay. This is called the Dendrogram Item because it allows the visualization of a tree of information. And we have a lot of different features associated with this visualization as far as subtrees of informations and selections and so forth. Here's another one, which is the Heatmap item, where we have a two-dimensional relationship between some species of data, some other ones, and then some scalar field that is visualized via color in the mapping. So the heat map really is multiple tables of data that are related between each other by a certain set of relationships. In this case, we have some XML encoding to express those relationships between the different data. And then we can finally connect together those two visualizations. We see here an example of the tree layout. So we have really here now a hierarchical graph of relationships. And then at the very bottom, at the leaves of the tree, we have this particular encoding of colors between the different items here on the left and on the upper side of the tree. So those are examples of some of the new InfoVis relationships available in VTK. Okay, I have an example here to show you. This is the third example in the list called test parallel coordinates color. And if I can get back to my view, there it is. There's an interesting example in the fact that it's a little bit unusual. It's called a parallel coordinates view. What this is showing is a data set with multiple scalar fields. And for each of those scalar fields, we use a particular x-axis. So here we have 4 of them. Yeah, this is x, this is cosine, sine, tangent, and we are connecting every dot, if you want, with the particular scalar field, the multiple scalar fields. We're connecting them with lines so that we can see patterns, if you want, in a planar 2D view. We can see patterns between the different functions. And then the interaction that is provided by the VTK, if I can get it to work here, it doesn't seem to recognize my mouse very well. No, it doesn't. The idea is that you can actually switch back and forth those different axes, left and right, and then you can limit along the scalar range vertical axis. You can limit the display of your variables. I will show you interactive demonstration with ParaView this afternoon where this works in a much easier way. In fact, I could do it immediately, since the interface here is not quite conducive to the demo VGL run. Okay, if I open this data set, okay, this is a typical data set with multiple scalar fields. We have, this is about cars. So we have the horsepower, HP. We have the weight. We have the year, acceleration, miles per gallon, etc. Multiple scalar fields related to this data set. Here in a spreadsheet view, so nothing new in this particular mode. However, if within ParaView I create a parallel coordinate view and I make the data set visible. Okay, there I have it. And I can, in principle, there we go, select one particular axis, move it elsewhere. So what I'm showing here, if we look at the first axis, for example, the first axis is the cylinder, okay? So this is a finite set of numbers. We have the automobiles with 4 cylinders, those with 6, those with 8. And in fact, we can see that from the 8, 6, and 4, actually we even have a data point at 3. We have multiple then lines starting from 4 and then going out to the other axis of the data. So this is by rearranging those axes and by limiting the axis display here, we'll be able to do some refinement on our data selection. Good morning, everybody. Welcome to CSCS. If this is the first time you are here, this is a big fancy building. You don't see any of the machines. The machines are in the other building. We might be able to get a tour later on during a break. I'll have to ask about this. But we're not here to look at machines. We're here to do some graphics and visualization. I am the visualization task leader here. I've used visualization for many years. I've used many different visualization applications. So why do I propose today the following softwares? Matplotlib, Visit, ParaView. It's because they're free, they're open source. But not only, because being open source sometimes means it's not well maintained, it's only one person in a remote part of the world doing a project. This is different. Matplotlib, Visit, ParaView, there are big projects maintained by a large community of developers and enthusiastic graphics and visualization users. So this is what I recommend. Furthermore, we are in a university environment, so I'd like to propose tools that people can just install very freely without having to require a license. That being said, you can have your favorite, one of your favorite tool at the end of this tutorial installed on your laptop, and when you travel to a conference, it's very easy. You want to show your work to a colleague, you open your laptop and you launch the software, and you're done. So no license, no. This is quite important, I feel. So already this is not working as I intended. The wireless, you've noted it already. So there's the agenda. Setup, objectives. Then we're going to look at this matplotlib library, which is a Python library to do 2D, mostly 2D, usually 2D graphics. The type of graphics you want for your publications, okay? Because it's actually very seldom that I see 3D visualization inside a publication. People expect a nice XY graph, a nice plot with nice legends, etc. That's what you need for publication. However, it's probably the case that to get to the 2D data that you need to plot, you have used some large 3D simulation behind it. And by the way, we are in a supercomputing center. So for me, when I talk about data, I assume the data is large. I assume you're doing some big computation. Otherwise, you shouldn't be at a supercomputing center, right? Now, how big is big? How large is large? Many years ago, my colleague Jim Ahrens from Los Alamos gave the following definition of large. And I think it fits quite well. Large is what doesn't fit on the computer you're using on your desktop. So if you have a fancy Mac with 16 gigabytes of RAM, large would be 20 gigabytes. If you're using a palm top, a hand device, large is probably smaller. If you're using if you're using a cluster, large will be perhaps a terabyte. And if you're using ROSA, which you can today at CSCS, and Daint, which is the next crazy supercomputer that will be made available for the public, then large can be petabyte. Okay, so what matters is what tool you're using to actually do your graphics. Matplotlib. And we're going to do some exercise, and here, of course, we have to start from simple things, so the people who have already practiced with it, bear with us. We'll take a break because all of us, including people here in Lugano, have gotten up early this morning to arrive, so we'll need a coffee and a break at 10:30. Then I will talk about visualization pipeline. Because it's an ubiquitous term, I will talk about pipeline, or I assume the notion of this visualization pipeline are known for the rest of the 2 days of presentation. When we will see the ParaView and the Visit software, they implement a visualization pipeline. However, it's hidden, which is good from the point of view of the user. However, many times, in fact, I have users tell me, this doesn't work, and yet I've done everything right. Well, it's because there are issues with this visualization pipeline that people completely forget, and then the system is not dimensioned correctly to actually do the visualization. We'll talk about VTK and some examples of charts and info visualization, because VTK, which is this C++ toolkit, which is more than 20 years old now, it's really a mature toolkit. VTK has also expanded into the realm of 2D graphics and non-spatially related data. So this is what we call the InfoVis data. We'll talk about data formatting because many times, especially new users at the computing center, will make, let me be frank, will make the mistake of inventing their own data format because it's just more convenient. I understand it, so there. I do it this way. But then we cannot use the visualization softwares we have available because we cannot read this data. So we're going to learn about how to write proper data to be able to facilitate this transition from simulation to visualization. And really, I said transition, but I always think about visualization as being an integral part of your simulation cycle here. So you run some simulation, you produce some data. Visualization is just one other step of your process. There will be a lunch break. And then we'll talk about ParaView. ParaView, so we only have an hour, which is not much. I've taught ParaView tutorials that were going on for 2 days, you can imagine. But the essential we're going to learn, and one of these essential things is how to use ParaView from your remote location, wherever you are in Switzerland or across the world. Then we'll talk about architectural issue and big data. We'll have a break, and then we'll talk about exactly this client-server business, how to run simulation remotely. And then finally, we'll talk about interactive session versus batch mode computing. Now, all of the batch computing we're going to do for the next 2 days is Python driven. However, you don't have to be an expert at Python. I am not. Okay, I tell you immediately, so you know the setup. But we need to know the basics of Python, and then we're going to use Python from this morning until tomorrow afternoon, everywhere, and we're going to learn how to have the visualization application write the Python code for us. This is why we don't need to be experts. The applications will write the code, and then we'll have to do some fine-tuning maybe